Okay, with this videos, I want to introduce the 3 experiments we offer in our lab for Control System 2 and for Identifikation und digitale Reglersysteme. This video should help you in the preparation phase and give you some hints in the execution of the experiments, because we have at this time, some Corona problems and distancing and so on. So I think this video should help to give you a successful possibility to close up this lab experiments. Okay, I go through the paper. I do all the things together with Mr. Stur, my lab engineer, and the paper is published in the Moodle courses. So you can have this and can follow me and do some things. We have 6 places with 6 experiments, where 3 experiments are just doubled. For example, experiment 2 and experiment 5 are absolutely identical, because the hardware we need is doubled, is copied, and we have just identical hardware. In the digital position controller, we have in main the same ideas and principles, but the hardware is totally different. In experiment 1, you work with a breathing system. In experiment 4, you work with a rack and pinion drive. So the numbers, the K's and T's are totally different, and the results are totally different, but the principles are the same. Finally, in experiment 3 and 6, there is the task to balance a vertical pendulum, but the drive is in experiment 3 a rack and pinion drive, and in experiment 6 a spindle drive. So the position control of the driving car are totally different, but then after this, the rest is identical and the principles is identical. So the main things of the descriptions are the same. So we start with a digital position controller, and I show you at the first picture of the experiment 1, the breathing system. Here you see in the upper part of the picture, you see a drive which comes from Trägerwerk, which is used there in an anesthesia breathing system for many years. There is a DC motor which drives our belt. This wheel is connected over an axis to 2 wheels here inside, and there is a belt who drives the encoder, the digital encoder for this axis. And finally, a piston here in this, a piston in the cylinder. And this is just a pump, where at the backside of this there could be a connection to a patient system, where the patient's lung is connected, and the air of this cylinder is then pressed and sucked out of the lung and into the lung. That's the main task of this hardware. In this experiment, of course, we don't want to do anything with breathing, but we want to move the piston backwards, forwards by driving this motor. So we have added an electronic which has just a simple amplifier for the motor, DC amplifier for the motor, and hardware which converts the movement here of the digital encoder into a voltage. So there is a voltage in and a voltage out, and that is connected to a PC, and the rest is done on a PC. That is the hardware of experiment 1. Now I go to experiment 4. Note this picture. Forget this pendulum. This pendulum is not connected, so there is just a driving car on a tooth belt, we can say. Just I have a bigger photo. Sorry. Here you can see it in more detail. Here is here you see the teeth there is a wheel running on this teeth, and there's a second wheel. The first wheel is the axis of a motor, so this is a drive. This wheel is connected to a digital encoder who gives pulses by movement, and these pulses are converted into a position voltage. And finally, this axis doesn't play any role in this experiment because this drive is used in experiment 3 and 6 for the pendulum, but here we use this just for a position control system. Yeah, so this is the hardware of the drive, and the principle is very simple. We have a closed loop system where a PC does a job. The PC has an ADC card with an AD converter and a DA converter. So there's a voltage coming out, going into a power amplifier, which drives the motor. The motor drives then the hardware, the process, and the position is measured then with a position sensor, and this is going back to the AD converter. In experiment 1, this is really a voltage. In experiment 4, this is really software, because this is just the encoder, and the encoder goes directly to the card, and the card produced directly a number. Yeah, so different sensors, but the principle now is the same. And the task of this experiment is to play now with different controllers and find differences, and you can compare the different properties of the different controllers. So in your preparation, you can see the diagram of a measured step response. We have done the job of measurement of the step response. So you see here is the time 0. Here the motor voltage is switched on with a small delay. Then you see a following ramp, and this ramp indicates that our process is an integrating process. Integrating, very simple. The physical reason for integrating is the position coming out of the motor connection is the integral of the speed. Yeah, or the speed is the first derivative of the position. So physical law gives the type of a process, and this delay comes out of the motor electronics. It's the motor itself. It takes some milliseconds before there is a real movement after switching on of the motor power. So we have a delay and a ramp. Identify this as an IT1 system, and then you have the process parameters. That's the task and the preparation. Use this diagram, or of course you can also download the files. Note that all files for these experiments can be found not in your CS2 and German course, but you have to go to the Toolprogramme Bayerline, and there you can find in the section of WinDFC#, there you can find a folder which contains all files of all experiments. So this is a third course you have to open. Then I have less work to store all these files or actualize files because these files are used in 2 groups. Sorry for this, but back to your job. Find out the K and the T. Note that the motor voltage for this input is different in experiment 1 and 4. The voltage of the motor, I'm not sure if I can find the values there. Stop, I have to check it. Okay, that was not at this time for sure for me. These diagrams, this is a diagram of experiment 4. You can find also this diagram for if you make experiment 4, you have to deal with this picture on page 25, or with the file step Sprungantwort of the blackrec.sim. That is the text file which you can load in my WinDF program. But again, you see this is a little bit different. The delay is a little bit larger. So this is the unit step response of the experiment 4, and the other picture I've shown just before is the unit step response of the breathing system. So find out the K and the T, and then design a list of controllers. You should do the design with the tool, the analog tool Rec C#. This IT1 is realized with a PT1 and an integrator. So put the K into this block, this integrator, and the T, the time constant, the delay, into the PT1. Then you have an IT1 system. Add, please, then a delay time block with 15 milliseconds, because we want to run the programs in real mode with 10 millisecond sampling time. So the delay is 1.5 times sampling time, so 15 milliseconds. And this is then the real process. Yeah, this is the dirt effect of the digital controller. This is a process designed now with Rec C#, 4 controllers in the manner here, what you can see in this block. 4 controllers with first a P controller with FRA design and 60-degree phase margin, a PDT1, a PI, and a PIDT1 with symmetrical optimum is necessary because the process is an integrator. You must use this, and use your TV, set this to your found identify time constant of the process, and use pole compensation here. So with FRA design or with Rec C#, click 4 times through the controller design mechanism. You should also program then in C code later. I'd explain this in a few minutes. Also PID controller with an anti-wind up function. Yeah, so we want to use with the K's and T's of the PID of case 3 and 5 are the same. And finally, you should design a classical deadbeat controller for an IT1 system. You can find in the paper of the lecture the equations to do this. Yeah, and we want to program also a deadbeat controller. So in total, you should program 6 controllers, design at home these controllers, bring on a paper or in a file all Q's and P's of 5 different controllers. Yeah, case 3 and 5 are the same Q's. And yeah, then that is the preparation phase, and then come into the lab. Then we will do the programming in a following mechanism. You work with WinDF C#. You get the source code running on Visual Studio 2019, the actual version of the compiler. If you are not familiar with this, it's not so important, because we will start this. Open the editor at the correct position, and you have only to know how to play with your controllers. For this purpose, in the toolbox where you can find your controllers, here you have the possibility to switch between my algorithms, which are built in, we have seen in the lecture, and the ready button stood opens the way to your program. So you can play with your controllers. You will see then here some radio buttons where you can select your controller and then play with the controllers. The operation with the WinDF C# I have shown in the lecture. Here you get some hints for setting. Of course, you should also play with the Richalet and the deadbeat controllers and find good settings to control your process, and then compare them. Yeah, that's the task. Okay, some hints here for the Visual Studio C compiler. Yeah, we start with the source code of NDF C#. You know this program in a way. I think you can work with this. In this project, there is a file, a module, form adaptive control. This will be opened by us, initialized, so that old student code is removed and you get a cleaned new part of the program. Look for this code. This is the code you get from us, which is running, and your task is then go into this switch case part, and here you should program your code. Some hints for the code is very simple. Here in the first lines, you see we have built functions for an ADC input and an DAC output. The ADC input delivers the actual measured position value in the variable val. The value gets the actual position, and here you store the y out value, which we have calculated in the step before, and send it to the motor. So this is a position input, this is a motor output, and then here the program calculates the control difference, because W is the desired value changed with the settings of the module for the user interface. This is the actual value, so this is the actual measured control difference. This goes into this switch case statement. Here the number in ncon gives, in the control of the framework, gives the number of the selected controller, and here you write just the lines of a P controller, PD, PI, PID, and so on. The coding can be done very simple by direct putting your Q's and P's as numbers in the code, because this is a quick and dirty method which is absolutely sufficient for this experiment. So don't make variables for Q0, Q1, and so on, and fill this with these numbers, because they will never change in your experiment, in your phase of lab. And note that the decimal separator must be in C# or in C or in any other computer language, must be a dot, a point, not a comma. Comma is different syntax. That's very often made as an error. So here you fill your 6 code lines, and note that you have, of course, to use some variables for storing old input and output values. These variables you can, of course, you have defined these variables like this, not inside this function, because then this is deleted after leaving this algorithm. You have to put this declaration outside of this function. Then this is used as a global variable, and you can store values from step to step. You should know this algorithm is called automatically if you start your step response. It's called each 10 milliseconds and left. So 100 times a second this code is executed if in the user interface you start the reference step response. So you need variables outside. The names of the variables are free. You can invent these names for your own. Note that a variable name in C# must start with a letter, and you should avoid special signs. So just letters and numbers. No parentheses or anything are necessary, because parentheses are used in the syntax, of course, for functions. So avoid in variable names parentheses, and please don't work with arrays. That is not necessary. Just for each variable you used for storing old values, just simple double precision floating point variables. That's what you have to do. So read this, and you should know that there is a limitation for Ymax. The Y out value is limited later in this program to plus to minus 10 volt. And yeah, you have to find an initialization for each new step response. All your storing variables have to be set to 0. You can do this in a function which is named by the program button run underline click. And this function, this is executed each time you click on the run button. So this is a good event where you can store 0 into all your variables, which stores old input and output values. Okay, if you are ready, then click on play, and then you can start your program. Yeah, one hint: if you declare your own global variables, here you see outside the function, of course, then these names must be different to names I used in my module. So my recommendation is make an underscore sign before your name starts. The underscore is the only special sign which is allowed in variable names. Then we can be sure that your name doesn't exist in my program, because then of course we get intermixing problems. Yeah, so your name should start with an underline and declared outside this program. So you have 3 positions for your write code. First position here. After the switch, you have to fill, of course, the content of these variables with old values, and initialization in the button run function, and that's all. Okay, if you have written your code, that is a phase between 20 to 30 minutes, then you start the real-time controller. First, in the ADC card menu, you have to select the National Instrument card DAQMX. That is the internal name of National Instrument for the interface. Click on the init button, and in the case of the breathing system, you have just and you have to connect with cables the input and output of the breathing system with your card. I think we will do this for you. So if you then play with this module, this init module, you can select, I can show you this just live. Stop both experiments, select in ADC cards the NI-DAC-MX module, and this module I of course cannot now click on init because this doesn't work on my laptop. I have no ADC card. But if you click on init, then you can play with a analog output 0. If you go up and down, sorry. If I go up and down with this value, then the motor voltage is changed, and then the piston or the motor of your card should move, and the card should move from left to right if you have a positive, or from right to left if you have a negative voltage. And here in the breathing system, here you measure the position, and in the rack and pinion drive you have to click on black card, and then this counter gives the value which is proportional to the position. Then you have to select the radio button digital output, and then you see this, and if you move by hand the position, this should change. Yeah, so this is just the connection of the PC with your hardware. Okay, so far. And yeah, before you start in the lab, you should play a little bit with the effect, a nonlinear effect, which has something to do with our position control system, because a motor, any motor in the world, has a dead zone, a so-called dead zone. That means if you look into this diagram, you have a motor voltage on the horizontal axis and the speed of the motor on the vertical axis. Mostly we have linear behavior here and in the other direction here, but in the near of zero we have a nonlinear effect called dead zone, and this nonlinear effect is caused by friction. And what happens if you start from 0 voltage and slowly increase the voltage is this: if you reach U2, then suddenly the motor starts movement, and then you are in the linear phase. If you then decrease the motor voltage slowly, then at some voltage U1, the motor stops. U2 is larger than U1 because this is caused by the static friction, and this is caused by the dynamic friction. Both values are different, and the same is in the other direction. You should play with the potentiometer at the motor voltage input a little bit and find out with a digital voltmeter the approximate sizes of these 4 voltages. So we need an information, and U1 is and U4 is the voltage where if your motor voltage is smaller, there is never a movement. U2 and U3 are that voltages. If you have voltages larger than U2 and smaller than U3, you have always movement. And here is a region where you can have movement or not. So this is a hysteresis, and hysteresis is not easy to measure, but I think take 10 minutes to play with the potentiometer to make U larger and smaller, and look for the movement of the motor and find out how large your voltages are. They are different in both experiments. Later we want to compensate this dead zone with a simple trick. Okay. Then in the rack and pinion drive, experiment 4, you make a 2 volt step from 0 to 2 volt. In experiment 1, you make a reference step from 1 to 7 volt. So this is different, but you will see this works very good. Okay, and then here are some hints for your lab report. That's information for the position control system. I want to see here 4 diagrams. You can print it out, list it on the computer. Your framework WinDFC#. You have seen this in the lecture and several experiments, stores different curves for different controllers in one slide. Then you can print out this slide with just a print button. I show you the print button. In your document you can fill printouts of our printer. So make here this print button, and then this picture here is then sent to our local printer in the lab. But of course, for your document, you can store on each computer, make screenshots directly in Word. As you should know, there is on each PC there is a Word Office installation. And in Word, you should know there is a possibility to make screenshots. Maybe you don't know this. I show you how to do this, because this is very simple to list all your pictures in your document. If you open Word, I start Word. Then if you go to Insert oder Einfügen in Deutsch, Insert, and there is a button for a screenshot. If you open this, if you click on Bildschirmausschnitt, that is a screenshot mode. Here you can, if you click on it, then you can select this, and I can, ja, das funktioniert jetzt natürlich nicht, ja. I can mark a rectangle, and then you have this rectangle in your Word document. So this, you should know, it's a very simple method to make documents. So make screenshots for your paper, because then this is a good way to create your document. Of course, you can send me your documents as PDF files at my email address. Yeah. So far, yeah, I think this should be enough for experiment 1 and 4.